Hey guys, for this lesson that we're starting today, we're going to be starting a whole unit on molecule shapes and structures and things called intermolecular forces. So what we're going to be doing today, we're going to be drawing covalent compounds. We're going to be drawing what's called a Lewis structure for covalent compounds. These were developed by an American scientist named Gilbert Lewis around very early 1900s is when he developed these. Uh, we're going to use them to help us gain some insights into the actual three-dimensional shapes of molecules and how that gives them some of the properties they have. For instance, we're going to learn why things like oil and water don't mix at the molecular level. So, first of all, we're working with covalent compounds, which I don't know how much of this you remember from many months ago, are made entirely of nonmetals. That's the things on the right hand side of the staircase line, plus hydrogen. Also, we're not going to be working with the noble gases because they don't really form compounds very easily. So we're working with a very small subset of the elements. Now, the first compound that we're going to try and draw is one that you're all familiar with. It's water, H2O. And in order to do this, we need to pick one atom to be in the middle, and then we're going to connect everything else to that atom in the middle. And for our purposes, the atom we're going to put in the middle is the thing we only have one of, which is the oxygen. So we're going to put an oxygen in the middle, and then we're going to put some hydrogens around it. The next thing we need to figure out is valence electrons. And valence electrons are the electrons in the outermost energy level of an atom. And if you have your periodic table, it's easy to tell how many valence electrons there are because that's what the little Roman numeral at the top of the periodic table represents. So, for instance, everything in group 1A has one valence electron. Group 2, with the Roman numeral 2, they've got 2. If you come over here, like the boron group, they've got 3. The carbon group has 4. If you're in group 15, you got 5. Group 16 has 6. Group 17 has 7. So since oxygen is in group 16 or 6A, it's got 6 valence electrons. Nitrogen has 1. So if we add up our total number of valence electrons, oxygen has 6, plus hydrogen has 1, plus the other hydrogen has 1, and we get a total of 8 valence electrons. Now, electrons in covalent compounds occur in pairs. And a pair is, as you might remember, 2. So if we divide this by 2, we get 4 pairs of electrons. Now, in chemical bonding, there's this thing that we're going to be following called the octet rule, which says that atoms want 8 valence electrons, except hydrogen wants 2. So hydrogen follows what's called the duet rule. Everything else follows what's called the octet rule. This is our general guideline. So each of these atoms, so each of our 2 hydrogens wants 2 valence electrons, and oxygen wants 8. Well, if we have 2 for hydrogen plus 2 for hydrogen plus 8 for oxygen, that would be 12 electrons that we would need. And we only have 8 electrons, or 4 pairs. So the way we're going to make this actually work is through sharing. So we're going to create what's called a bonding pair of electrons between the hydrogen and the oxygen. And we're going to represent that with a line. So that represents one pair of electrons that's shared between the hydrogen and the oxygen. So that means that this hydrogen here has one pair of electrons, and this hydrogen here has a pair of electrons, or 2 electrons, and this oxygen right now has 2 pairs of electrons, or 4 electrons. So the only thing we have left to do in order to satisfy the octet rule is this oxygen needs 4 more electrons or 2 more pairs of electrons. And so we're going to add those on. And the way we add on extra electrons, we're going to have our general rule that for electrons that are shared between 2 atoms, we represent as a line, and electrons that are just on a particular atom, we're going to represent with dots. So for our other 2 pairs of electrons, we're going to represent them like so. So this represents our 1, 2, 3, 4 pairs of electrons. Hydrogen has its 1 pair or 2 electrons. This other hydrogen has its 2 electrons, and this oxygen in the middle has 1, 2, 3, 4 pairs or 8 electrons. And so this would be a Lewis structure for a water molecule. So I know that's a lot, maybe a little confusing, so let's look at a few more examples. Let's consider carbon tetrafluoride. So in this molecule, since we only have 1 carbon, we're going to put carbon in the middle. We're going to put the fluorines around it. And if we check our reference tables, carbon has 4 valence electrons and fluorine has 7. So the carbon has 4, plus each of the fluorines has 7 valence electrons. So we add all those up, and that's going to give us 32 valence electrons, or 16 pairs. It's a lot easier just to count pairs. So the first step, once we've got our general layout, is we need to connect each of the fluorines to the carbon in the middle with a bonding pair. So we're going to go 1, 2, 3, 4. That's 4 of our 16 pairs of electrons. Now, this carbon in the middle has already satisfied the octet rule with 2, 4, 6, 8 electrons. So now we just need to use our other 12 pairs, because we have 16 total pairs of electrons, to satisfy each of our fluorines. So each of our fluorines needs 6 more electrons or 3 more pairs. So we're going to just add them on. Just like this. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs of electrons, and everything has 8 electrons around it. So we have managed to satisfy the octet rule, and this is what a Lewis structure for carbon tetrafluoride looks like. So now let's look at a few more. You may remember that all of the halogens, that's our group 17 elements, they always occur in pairs. They're diatomic. So let's consider why that might be. So let's consider bromine, the Br2 molecule. Well, we've got 2 bromines. Each bromine has 7 electrons. So that's 14 valence electrons, or 7 pairs. So if we draw this, that's going to go 1 pair, 2, 3, 4, 5, 6, and 7. So the reason the halogens all occur as diatomic elements is that by sharing 1 pair of electrons between them, each of these 2 atoms satisfies the octet rule, which puts them into a very stable chemical formation. So each of the halogens, each of our group 17 elements, would work exactly the same way. Now let's look at one that's a little more complicated. Let's look at oxygen, which you might be aware occurs as the diatomic O2 molecule. Well, if you have 2 oxygen atoms, well, they have 6 plus 6, or 12 valence electrons, or 6 pairs. as you might would guess. So if we go 1, 2, 3, 4, 5, 6, we've drawn all 6 pairs of electrons, but this oxygen over here is short a pair. It's only got 2, 4, 6 electrons around it, while this one over here has 2, 4, 6, 8 electrons around it. That's a problem. So we can solve this by seeing if this oxygen here could maybe share another pair of electrons with the other oxygen. And so we can take away one of these pairs of electrons and share it. And we end up with something like this. And that is what we would call a double bond. So by sharing 2 pairs of electrons, these 2 oxygens are able to achieve the octet rule as well, because each oxygen has 8 electrons around it. 2, 4, 6, 8. 2, 4, 6, and 8. And that's the way the oxygen atom actually exists, is it is a double bonded molecule. We're going to move on to one more example. The N2 molecule, or the nitrogen molecule. And nitrogen has 5 valence electrons. So that's 10 valence electrons, or 5 pairs. So we go 1, 2, 3, 4, 5. That's all the electrons, but this poor nitrogen over here is short 2 pairs of electrons. So what we can do is we can actually share 2 pairs of electrons from this other nitrogen. Making a triple bond. And for those of you who like symmetry, we can take this lone pair of electrons over here and put them on the end to get this, where we have a triple bond. And in case you're wondering, triple bonds are as high as you can go. You can't fit 4 pairs of electrons in between there. There's just physically not enough space in between 2 atoms to fit 4 pairs of electrons. But this triple bond is the strongest chemical bond that exists in nature. And for those of you who remember back to earth science or biology, learning about the nitrogen cycle, your bodies need nitrogen in order to make things like the nitrogen bases, the adenines, thymines, guanines, cytosines that are in your DNA. DNA involves nitrogen in it. And your body is incapable of separating one nitrogen atom from another nitrogen atom. But there are things called nitrogen-fixing bacteria that are capable of breaking apart that very strong bond. And so in order for you to get the nitrogen in order to produce your DNA, you can't just breathe it in, because nitrogen actually makes up 78% of the atmosphere. But your body can't use it in that form. So instead, you need to get the nitrogen to make DNA from your food, where it consists of nitrogen that's bonded to other things without that triple bond. So just a neat little thing about nitrogen. I'm going to look at one more example that builds on this and makes things a little bit more complicated. And then I'll turn y'all loose to try a few on your own. So the last thing we're going to consider is sulfate, SO4, with a -2 charge. So we're going to put sulfur in the middle. We're going to put some oxygens around them. And if we check our reference tables, both sulfur and oxygen are in group 16. So they have 6 valence electrons. So that is 6 plus 6 plus 6 plus 6 plus 6. Add all that up, 12, 24, that's 30 valence electrons. We need to address this -2. What that -2 means is that we have added 2 electrons. Because electrons, if you'll remember, are negatively charged. And so if we've got a -2 charge, that means we've got 2 more negative charges. So on our electron count, we will add 2 for 32 valence electrons, or 16 pairs. Now that's confusing that a negative charge means you add electrons. If we had a positive charge, we would subtract electrons. But the way we do this, to draw it 16 pairs, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that's all the pairs that are needed to draw this. And the last thing that we're going to do to represent that this entire molecule has a -2 charge, so we're just going to put some big brackets around it and put a -2 on it. So that's how we draw some Lewis structures. Tomorrow I'll show you some more complex Lewis structures, but I want to give you the opportunity to practice these now, and then later on I'll post a video where I actually work through the worksheet with you so that you can kind of follow along, but I want you to try it on your own first. So good luck. Greetings, chemistry students. Today I'm going to show you how to draw some more advanced Lewis structures than the ones that you learned about yesterday. So make sure you check out that first video, because today we're going to do a little bit more advanced. So let's go back to a problem that we had on yesterday's worksheet, which was the NO2 minus 1 molecule, where when you drew it, kind of looks like this. We've got 6 electrons on each of our oxygens, 5 for the nitrogens. That's 6 plus 6 plus 5, which adds up to 17. Then we also have that extra electron for the -1 charge. That gives us 18 valence electrons, or 9 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we have a problem because the nitrogen is short a pair of electrons. It's only got 1, 2, 3 pairs, or 6 electrons, and the octet rule says you need 4 pairs, or 8 electrons. So we can borrow a pair from either one of the oxygens. And if we borrow one from here, then we make a double bond on that side, or we could have done it the other way and made the double bond with the other oxygen. Now, the thing to note is that double bonds are shorter and stronger than single bonds. Double bonds are shorter and stronger than single. And as you might guess, a triple bond is even shorter and even stronger, which is why nitrogen fixing bacteria are necessary for us to live. But if we go back to this, if we have a double bond in one place and a single bond in the other, you would expect that this bond is longer than this bond. Now, scientists have some specialized techniques called spectroscopy, where they're actually able to measure the bond lengths. And when they do, they find that both bonds in this molecule are exactly the same length. And they're pretty much halfway in between the length of a single bond and a double bond, which implies that we don't actually have a double bond in one place and a single bond in another place. We've actually kind of reached the limitations of the Lewis model. But what that kind of implies is that what we have is kind of a mixture of the two. Instead of having a double bond in each place, it's more like we have a 1.5 bond in each place. Now, the way we draw this is we draw what's called a resonance structure. Where essentially we draw both possibilities when put them in the square brackets and just put a double arrow in between them. We also need to add the -1 charge because this thing was negatively charged. So this is our resonance structure. It's not that there's a double bond that's moving back and forth. That's not what's happening. It's that reality is like a composite of both of these. Now, you might ask us, well, why do we even use Lewis structures if they have these limitations? And the reason is, as you'll see in our next lesson, Lewis structures are really good at predicting the actual three-dimensional arrangement and shape of a molecule. So that's why we still hang on to these, even though it's not a perfect picture of reality in a molecule. I'll move on and show you another example. In this case, we're going to look at the sulfur trioxide molecule. This is not sulfite, SO3 with a -2 charge, the polyatomic ion. We drew that in the first Lewis worksheet. This is sulfur trioxide. So we've got a sulfur, we've got 3 oxygens. We add up our electrons, 6, 6, 6, and 6. That all adds up to 24, or 12 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have drawn all the electrons we have, but this sulfur in the middle only has 6 electrons around it instead of the 8 that it needs. So it could make a double bond with this oxygen. This oxygen can share a pair, or this oxygen can share a pair, or this oxygen can share a pair. You might guess where this is going. What we're going to end up doing is drawing all 3 possibilities. So we've got the double bond on the right-hand side. And then we could also draw the double bond on the bottom. Put some brackets around it. And draw some arrows in between. And these are the 3 resonance structures for the SO3 molecule. And you'll never have to draw more than 3 resonance structures in this class. Now, I do want to also point out to you there is a difference between SO3, sulfur trioxide, and then sulfite, SO3 with a -2 charge, because you may notice from yesterday's worksheet, we didn't draw this resonance structure. We had an extra pair of electrons to put right there on top of the sulfur, which, as we'll learn soon enough, gives it a different shape. We're going to look at just one more example of this. This is a molecule I like to talk about. It's the O3 molecule, which is ozone. And we've got 3 oxygens, each with 6 electrons. Add them up, it's 18 electrons, or 9 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And the oxygen in the middle is short a pair, so we can either make the double bond on the left, or we make the double bond on the right. We draw both possibilities. There we have it.